Security is a huge topic that we can probably talk about for ages. For now, I'll try to limit myself to the basics. In this first part, we'll discuss the basics of security and certificate pinning. Before we begin, I'd like to make a short disclaimer. Security slows stuff down and sometimes makes your app more cumbersome. The question of why we didn't solve security is a question of usability. A lot of core concepts in programming would become harder and less efficient. This would also impact usability to the user, who often is the biggest vulnerability there is. Throwing permission prompts at users is problematic. It triggers permission fatigue, and users tend to ignore these prompts at some point. For programmers, things as basic as mutable state can often cause a vulnerability in code. Removing security weaknesses is pretty difficult. If you are still with me, let's start with the basics and common terms. A term you should all be familiar with is vulnerability. We hear that term a lot when discussing security, but it's a bit confusing sometimes. A vulnerability is a security bug, but that doesn't mean anything. All software has vulnerabilities because it's so hard to avoid. For instance, if you have a method that returns a Java array, your code is probably vulnerable. A caller can change the element in the returned array and impact internal state. Working around this vulnerability by creating a new copy of the array will be expensive. Most of us are willing to risk security for extra RAM and CPU power. An exploit converts a vulnerability or a few different vulnerabilities into a hack. So if you offer a banking SDK and return internal state in an array, I can then change that internal state and hack the SDK. That's an exploit. There are different grades of exploit, and sometimes you will need to chain them. The worst kind of exploit is a remote root exploit. A remote root exploit is a vulnerability you can use for full control of a system without physical access to the machine. That's the worst kind of exploit, and it's pretty rare. Usually, security works in layers, where penetration of one layer isn't enough. You would still face another layer below it. So let's take the example of returning internal state data and continue with that. Let's say one of the objects in the array has an OS native method. Let's say that method has a vulnerability that allows us to step outside of the virtual machine. The OS should have restrictions too. So even if we can step outside of the VM, we'd still be in a sandbox. Let's say the OS has a user escalation vulnerability where the attacker can elevate his privileges to root. So something small like returning an array can become the missing piece in a big attack. This isn't common, as such vulnerabilities are usually fixed by vendors. Our chief concern as developers is the safety of our app data and access, more than device root exploits. Codename One tries to be as secure as it can be by default. Some of our design choices make Codename One more secure by default, even when compared to native coding and especially when compared to other approaches. The first is obfuscation by default. Codename One obfuscates its code. This isn't a complete roadblock to a hacker. A diligent hacker can get around obfuscation. Still, it makes reverse engineering an application harder. Obfuscation is especially hard to deal with in Codename One, even compared to native code. Both Android and iOS store UI data in readable formats. Reverse engineering tools can decode these UIs by default. A hacker can point at a button and find the code that binds to that button. This undermines obfuscation in native applications. In Codename One, even if you use the GUI builder, the UI compiles to bytecode and thus to native. So the UI gets obfuscated with the rest of the business logic code. This means you will have more code but no readable layout files. Reverse engineering tools will have nothing to go on with Codename One. Even when tools adapt to Codename One, this is unlikely to change due to code obfuscation. In that sense, Codename One is even more secure than a typical native app. Think about the way a typical hacker will crack your application. Let's say you have a login button and the hacker wants to grab the username and password. The hacker can upload a hacked version of your app to the store and grab the credentials from a fake app. Users of the fake app will be oblivious to the steal, as the app will look and behave the same way. The first step to hacking an app this way is to find the button and fields code. In a native app, this would be doable, as both would be in the XML, so the hacker's job is trivial. For a Codename One app, this would be a tedious process of digging through obfuscated code. Finally, release builds add a few layers of default security, for instance, blocking remote debugging, etc. This is especially true for Android. As I mentioned before, we try to be secure by default. However, some potential vulnerabilities would impact usability too much. The first protection system I'd like to discuss is certificate pinning. Certificate pinning thwarts a man-in-the-middle attack on SSL. To understand this, we need to understand SSL and man-in-the-middle attacks. When we connect to a server, there are many servers along the way. For instance, if your user is in an internet cafe and a hacker hacked the Wi-Fi server, when he connects to your server, the hacker can spy and even change all of the communication. We use SSL or HTTPS to encrypt all the data, and this works by sending an encryption key from the server to the client. What if the hacker sends his own encryption key? That's why we have a certificate authority. You can't create a certificate for yourself. You need an authority to verify your identity. For instance, I can buy a certificate from VeriSign, who will verify my identity. That way, the client knows the certificate can be trusted. The problem is that certificate authorities got hacked in the past. So it's possible a hacker would get a valid, trusted certificate. In that case, he can execute a man-in-the-middle attack. This scenario is pretty challenging. A hacker would need to get in the middle. He would also need a valid fake certificate. This is a case that would be possible in the age of government-sponsored hacking. If you are building an app for the government or financial institutions, you should be aware of this. In those cases, you should use certificate pinning as an extra layer of security on top. Certificate pinning verifies a certificate signature of the server. We can thus verify that the certificate we are communicating with is a specific one. The downside for this is updates. If we update the certificate on the server, we need to update the installed applications. They might stop working or start warning users in valid server update situations. The connection request class contains a check SSL certificates method that accepts an array of the certificates supported by a secure connection. You can verify that a signature of a server matches a specific signature that you expect, and that way prevent a potential exploit. You can loop over the array of certificates and verify that a proper certificate is in place. The certificate unique key you get in the simulator should match the one you have in production. The drawback of the security layer is inflexibility. Normally we can just replace the server and set up a new certificate. As long as the certificate is valid, this is pretty seamless. But with pinning, we need to jump through a few hoops. That might mean that if you update the server, apps that are installed on a user device will stop working. Another important bit is the algorithm used. Most servers support multiple signing algorithms for maximum compatibility. However, algorithms such as SHA-1 are already long in the tooth. SHA-1 can be defeated with modern hardware, and it might be better to pin a stronger signature, such as SHA-256, etc. Every certificate has an algorithm associated with it, and you should pick the best option. Notice that you shouldn't depend on the number of certificates or their offsets, as this will block the flexibility of the server team to make changes.